Hey everybody, welcome back. C.M.4, still talking about circular motion, still using Newton's second law, centripetal forces, looking at the sums of those forces for things moving in a circle. Here's just the new scenario, bank turns. Oh my gosh, here's your warning. This is a math-heavy video. On the bright side though, the toughest of the math, it's very, very rare on the AP Physics 1 exam itself, but to be honest, depending on your teacher or your professor, depending on how you're watching this video, they might include these types of problems. If you're in my own class, you might see one of these really tough problems maybe once. Some of the key concepts, though, are important, and at least understanding the basic math is a little important, even if it's not necessarily always going to be on the AP exam. Okay, let's go ahead and get started. What do I mean by banked turns? It kind of describes a type of turn that an object can have, okay? Now, I have these three different images, all representing not a flat turn, but a banked turn. Think of the road or the surface curving upwards, okay? These two images are actually representing the same road. This is a test track in Germany, okay? And they have this road angled upwards. Similar type thing for a stadium where a bicycle race might occur. Okay, if you've ever watched NASCAR or F1, Indy racing, anything like that, a lot of the tracks will have these bank kind of curves. And why? We're going to understand why and, of course, analyze the physics. Well, a little different, still somewhat similar, is the idea of a plane banking. Of course, when a plane is flying and it needs to turn, it doesn't just go like this. It makes this bank for very similar reasons. Actually, seeing this problem on the AP exam might be a little rare. We're going to focus on cars, on bank tracks like the three images above, but the same kind of physics can be applied, okay? So what's going on? What's the difference between this and the curve we've already seen? Here's a reminder image when we were talking in the last set of videos, or the last video. If we have a car that's on nice, flat, even surface, well, it can turn, of course. Now, if it's turning, that must mean there's a net centripetal force. There's a net force towards the center of that circle. So in this diagram, this car is curving around like such. The radius is towards the center of that circle. What force is acting on it, causing it to turn in a circle? It's a frictional force. They're still normal in weight, but while those are acting, of course, vertically, it's the frictional force that's still acting, or that is acting, towards the center of the circle, okay? Remember, if I want to move in a circle, you have to have a certain amount of force. Remember how we kind of thought about what does it mean, this net centripetal force, mv squared over r? So you want to move in a circle, you need a certain amount of total force based on the speed you want to travel and the radius, how kind of tight that curve is. Before, in the last video, it was the friction that had to provide all that force. What's the benefit, though, of a bank turn? Well, if you think about it, our free body diagram before looked like this. But if I now maybe drew it for this car, yeah, there's still, of course, the weight force acting downwards. There's still mg. There still might be a frictional force. But remember, normal force is always perpendicular to the surface. So now my track is like this. It's almost purely vertical for this car. Perpendicular would be like this, okay? Now, do you understand the benefit of having a bank turn? Now, you're not relying on just friction like we were for a flat turn, but now the normal force is acting towards the center. Oh, now with a bank turn, in addition to friction, you might have additional forces that could allow you to move in a circle. That means you have additional sources that could provide a force to maybe allow you to go faster or maybe a sharper curve. They could add up to provide more centripetal force, therefore having a stronger curve, so to speak. So that's the idea. A bank curve now makes a part of the normal force acting towards the center, okay? Here's another diagram, and I like this diagram because it shows what it means for something to be moving in a circle on these bank turns. Now, this is actually a slightly different diagram. This car is kind of moving towards outside of the screen. This picture is going into the screen, but they both have the same kind of incline, okay? We're going back to inclined planes because even though we're obviously talking about things moving in a circle, if I took a snapshot of this car, and imagine I took a knife and just like I was slicing through a cake, I sliced through this bank. Notice what I have. I have a car at some angle. Well, that's very similar to when we were approaching cars on some kind of incline. So we're actually going back to inclined planes a little bit. So we're going to use the same kind of braking forces down into components, the same kind of SOHCAHTOA that showed up before, now for things moving in a circle. Now notice that the normal force is perpendicular versus when we were looking at it at the last video. There's a component that's acting towards the center. And to be clear, the center of the circle is not down like this. No, some students think that in the beginning. The car is moving in a circle in this horizontal plane. I like this diagram right here. There's no physical thing at the center of this circle, but the car is, if it stays level on this track, right? It's not going up or it's not going down. If it's staying level on this track, the plane of this circle is some horizontal setup. So the center is, if I was to go with orange, is like this. The center is in this direction here. Again, there's not anything physically there, but now when we set up the sums of the forces, we're going to look at the sum of the forces vertically and the sums of the forces centripetally, towards the center and vertically like we've done before. Okay, let's just jump right into it. We're not going to actually find any numbers. Let's just set up some algebra. So same kind of diagram I had as before, okay? Here's that same free body diagram. I have a normal force and I have mg acting down. We're going to start in part A without friction. Another benefit of these bank turns, if the normal force is providing that centripetal or a center-seeking force, maybe you don't even need friction to still move in a circle. That's what these first problems, that's what these easier versions are going to show. So, okay, so I have this object moving in a circle. Here's that normal force. I've drawn my free body diagram. The center is like this. So, normally what we would do, if I want to set up the sum of the forces in the centripetal direction, well, it's not the normal force. It's a fraction of the normal force acting towards the center. This right here, I'm going to label NC. Normally, I don't like doing this on the actual free body diagram. Remember how like we would draw our forces separately? We didn't often do it for the normal force, but we can now. The normal force has two components. It has this vertical component like this. I can still call that NY. And it also has now a force acting, left or right, admittedly, but now that's in the centripetal direction, like this, NC. If you remember, when we were breaking down inclined forces in the past, I said if you started in the Y direction with the Y component, that ends up being theta right there. That's not the only way. You could also have drawn it like this. You could have gone like this. Here's the normal force. Here is NC like this, NC. Here is NY. But you have to be careful. This would end up being theta. Theta, with respect to this little angle of the incline, it's where the hypotenuse is meeting that Y component. I know it's been a while, depending on when you've watched this set of videos on inclined planes, but it's that angle with respect to that vertical component. So what is the centripetal force? It's the component of the normal force. That's equal to MAC, or mv squared divided by r. And what is this NC? Well, it's the opposite side of my angle, the opposite side. If you have to bust out SOHCAHTOA, that's okay. So if NC, this centripetal component, is opposite, and the hypotenuse is over here, that means that NC is equal to N times the sine of theta. That means I could right here put N sine of theta equals mv squared divided by r. Now let's say I didn't know what the normal force was. Oh my gosh, how do I do that? Do you remember? Uh-oh. Oh, bad memories maybe. You look at the sum of the forces in the Y direction. That's NY, the vertical component of the normal force, minus mg equals ma times y. Okay, m times the acceleration in the Y direction. If the car's not launching up or down this incline, that's equal to 0. I deleted that other breaking into components just so I had a little bit more room. And y, what is that? That's adjacent to theta, adjacent. That's n cosine of theta equals mg. I could swing this mg over. Therefore, n is equal to mg divided by cosine of theta. So, oh my gosh, I could even all the way back plug that in. So I have that mg divided by cosine of theta, going back to green, multiplied by sine of theta equals mv squared divided by r. That would be mg tangent of theta equals mv squared over r. That's a lot of math. I get it. I know. But luckily, that's the challenge. It's the math challenge. It's the same physics as before, right? Setting up Newton's second law. Also, even if you get bogged down in the math, think about what this equation I wrote, what it means. Remember, mv squared over r. So you want to move in a circle. Well, you need a certain amount of force. What is this side of the equation telling me? if I have a steeper angle, because when theta is larger, tangent is larger, up to 90 degrees. So a larger angle would supply more force. You could maybe go at a higher speed or a tighter curve. And that makes sense. If you had a really banked turn, well, and then, man, you'd have a lot of normal force that could help you really arc and turn and curve. A smaller angle, maybe you wouldn't have enough normal force. Maybe you had to go back and rely on friction. So I know these are tough, but again, it's the same thing with inclined planes. Draw that free body diagram. Okay, set up the sum of the forces in the centripetal. You probably have to break something down and then wade through that trigonometry, okay? So those are the easier versions, these bank turns without friction. You don't need friction for a car to move in a circle if the turn is banked. But you could go even faster, or you could have even more force if you had not just the normal force, but friction as well. So again, there's that image again. Here's that car going in a circle. We just saw that the normal force can provide a centripetal force, but also if there was friction on those tires, I'll draw it there again, here again. Well, here, if I think of my free body diagram, I have a normal force that has a component going towards the center. I have weight, weight's not going to help us, but I'd also have a component of friction. Even more forces. That means even more ability to move in a circular path. Couple of things you got to remember. Centripetal, that direction is always horizontal. And you also have to remember that friction acts parallel to the surface. That's why I drew friction like this, down at some angle. Because friction, like we saw back in inclined planes, is always parallel. So let's set up a problem with this kind of physics that has both a normal force and a frictional force. If you thought the last slide's math was bad, you're not going to enjoy this. But try your best to stay with me, okay? All right, here's our diagram. Let's say there is friction. Now, of course, there's friction between all the tires, but we're going to simplify that as a single force. Our free body diagram, there's a normal force like this. There's weight acting down, mg, and there's a frictional force going in this direction. All right? If I want to set up the sum of the forces in the centripetal direction, well, there's a component. If I redraw the normal force, here's N. I'm going to switch over to green. Here is a component of N that is in that centripetal, right? The car is some radius away from the center of some circle. There's NC. Here is NY. NY. Technically, this would be theta right here. But if I'm setting up the sum of the forces in the centripetal, I would want to include the centripetal component of the normal force. And let's break down the frictional force. Well, if this is the frictional force, remember, parallel to that ramp, this right here, there's that component that's in the centripetal. This has to be theta, okay? Because right here, if this is F that's acting towards the center, this is alternating interior angles. So that's theta right there. And this downward component, I'm going to move my F over. So the actual friction F is right there. This right here is F in the Y direction. Would I add, if I'm looking at the sum of the forces in the centripetal towards the center of the circle, should I be adding this component of the normal force with this friction, or should they be subtracted? They should be added. Both are acting towards the center, plus FC. That is equal to MAC, or mv squared divided by r. This is why it could be even better, so to speak, right? If you want to go in a circle, you need a certain amount of force. Well, now there's two forces that could be providing that net centripetal force. Again, that's why if you had both of these, maybe you could go even faster or an even sharper turn because you have more opportunities to meet that needed force requirement. Okay, what is NC? Let's break up that trig again. Again, this is the side that is opposite. So that's going to be N sine of theta. Plus, what's the trig for the frictional force? This is adjacent. That's F cosine of theta. That's equal to mv squared divided by r. You could go one step further. I'm going to stick with red. N sine of theta plus, what's friction? Friction is equal to mu times the normal force. That's mu times n cosine of theta equals mv squared divided by r. What if, you don't know the normal force? We could set up the sum of the forces in the y direction. You see, it quickly flashed on your screen. I moved over that breakdown of the yellow FC, the frictional force, and I moved the equation for friction over because I need room. If I didn't know the normal force, the sum of the forces in the y direction. What forces are in the y direction? There's Ny. I would subtract Mg. Would I add or subtract Fy? I would subtract. If I'm saying that upwards is positive, minus Fy. If the car isn't accelerating up or down, it's not sliding down the ramp, it's moving in this nice circular arc, well, that would end up equaling ma in the y direction, or 0. What's the component of n in the y direction? That's the adjacent side. That would be n cosine of theta minus mg minus, what's the component of the frictional force? Fy. Fy, that's opposite. That'd be f times the sine of theta equals 0. And again, n cosine theta minus mg minus mu times the normal force, sine theta equals 0. Or you could write down n is equal to m times g divided by cosine of theta minus the sine of theta. I admittedly am skipping a step. If I added mg to the other side, and then I factored out a normal force, that's how I could get this equation. Okay, you could hit pause and stare at it if you want, but then I could have an expression for the normal force. I could plug that all the way back into here and here. Oh, if this shows up on your homework, your teacher doesn't like you. Or at least if they put this on your homework, a lot of times they don't like you. Okay, if you're in my own class, the odds of this type of problem being on your exam is pretty slim. Certainly bank turns without friction, that's not too bad. Okay, a bank turn with friction as well, it's an algebra mess. I know it's a pain, I know it takes a long time, but to be honest, again, it's the same physics. Free body diagram. Okay, what are your positive and negative directions? Break things into components. It would take time, I know, but you could do it, all right? That's the idea. Again, you want to move in a circle, you need a net force toward the center. This is just showing how now we could have other forces acting towards the center of that circle and the algebra mess that it could lead us with. But that's all, okay? Use this video as a guide. Come back if you need to for these problems, but I'm signing out. That's all. See you later. Thanks for watching.